this scenario, we are looking at a metal bar here that is an external field, magnetic field specifically, that is pointing into the page, and we are going to move that bar to the right. So if we use our right hand rule, we're going to point our fingers in the direction of the velocity. We're going to curl around and grab the bar because the magnetic field is pointing into the board. So our thumb is going to point up. So that's going to create a magnetic force that's going to push in the positive Y direction on the positive charges. So we're going to look at the magnetic force equals the charge times the velocity times the magnetic field strength. I'm not worried about the cross product because you can see that V and B are 90 degrees from each other already, so we don't have to worry about components in this case. Now, this is not a complete circuit. This is just a metal bar. So as we push the positive charge towards point A, that's going to cause charge separation, which is going to create an electric field that points in the opposite direction, opposing the motion of those charges. So we're going to have an electric force that is Q times the electric field, very similar to mass times the gravitational field strength. And those charges are going to move until the electric field that's generated balances out the magnetic force. So until we get this scenario here, where they are equal and opposite to each other. So subbing in the equation for the magnetic force, subbing in the equation for the electric field, we see that the Q's cancel out and we get the electric field is equal to the speed. Remember, that's the speed of the moving bar, not the speed of the charges, times the magnetic field strength. From Unit 1, we know that potential, in this case not velocity, is equal to the integral of E dot dl. So we're going to integrate over the length of the bar, which gives us this relationship here, where L is equal to the length of the bar. So I'm going to sub that in for the electric field. And then I'm going to rearrange. And rather than talking about potential difference or VAB, we're going to write it in terms of the EMF. And this is what we refer to as electromotive force. So what we would do with this is, instead of just having the metal bar itself, we would attach the metal bar to essentially a metal U. So this would be point A, this would be point B. We would have a magnetic field going into the board again. And rather than gathering here, so this tracks would extend further, so we would move this bar, and rather than gathering here, we would find that the charge actually moves through the U, and you end up with a complete circuit. And essentially, this is another way of seeing that induced current, where instead of the induced current being due to a change in magnetic field strength, it's due to a change in area, because the bar area is either getting bigger or it's getting smaller based upon the direction you move the metal bar. So if you guys were wondering how on earth I would ever change the size of the loop, when we talked about Lenz's law, this is one way to do that. So this equation here is another restatement of Faraday's law. Now, if V and B aren't actually 90 degrees from each other, there is another method of calculating the induced EMF. That still does have the cross product in it.